Welcome. This is the Module 2 lecture on chemistry. So let's go ahead and get started here. Slideshow, laser pointer. Alrighty, so Module 2 is looking at the chemistry of life. And here we have a beautiful periodic table of the elements with the actual elements in them. So I guess if you have a lot of money and know the right people to get all these elements, you can have one of these in your lab, your home lab or something. I think this was actually at a school in England where they built this display, but it's pretty cool. And you can actually collect all these elements if you're so inclined. So to start out the chemistry module, I want to remind you, never trust atoms. They make up everything. Okay, yes, chemists have the worst jokes, and I somehow feel compelled to share them. All right, so before we get started, just a few definitions to talk about. When we're talking about elements, we're talking about substances that cannot be separated into anything simpler that still retains all those properties. Yeah, if there's a mixture of elements, we could maybe separate them into their constituent atoms, and then once we have those atoms of those elements together, we cannot subdivide them any further and still end up with those properties. So really, atoms are the smallest unit with all the properties of a particular chemical element. Sometimes we might put two elements together and we end up with something completely different, which is either a molecule or a compound of those different elements. And we'll talk about what those, give some examples of that later on. But if we have two elements that don't react, then these definitions hold up pretty well. But really all the interesting things about chemistry are the reactions and the new properties that we see in those molecules. So I guess maybe I should have put molecule on here as well, but that's okay. We're getting ahead of ourselves. So to start with, what do atoms look like? Well, I've never seen just one of them. I've seen collections of atoms. Sure, I think we all have, right? But in general, if we were to pick out an individual atom for a particular chemical element, it might look something kind of like this. This one actually, I think, is helium. If we zoomed in on it with a super powerful microscope, we can't actually do this actually, but if we could, we might visualize that there's maybe four big, bulky, massive particles in the nucleus of the atom, so at the center, and then there are two very light, very small particles that are orbiting that nucleus, and those would be electrons. So the nucleus is going to have neutrons and protons. Those are the subatomic particles, which means smaller than an atom, right? The protons are positively charged and have a mass of 1 atomic mass unit, or 1 Dalton, if you prefer that. Neutrons are, as their name implies, they have no electric charge, but they also have a mass of basically 1 atomic mass unit, or 1 Dalton. And then the electrons that are zooming around in these shells of energy surrounding the nucleus, they have a negative charge and a negligible mass. they actually do have a little bit of mass. It's maybe 2,000 times smaller than a proton or a neutron, roughly. But for our purposes, we can ignore that mass. So that's the structure of an atom. All right. So what's this whole thing about this periodic table, and why do we need to learn all this chemistry if we're biologists? Anyway, well, I like to simplify the periodic table to basically how organic chemists see it. So we have carbon, the star of the show. That's maybe the most important chemical element for life as we know it. There's carbon's little buddy up here in this corner, also known as hydrogen. Over in the other corner is the sun, also known as helium, which is that atom we were looking at before. Then there's these block of elements where we need these to live. So those are also going to be important for our studies this term. Then there's all the other things. And I'll maybe explain this more during one of our lecture meetings. The don't get them wet atoms are things like lithium and sodium and potassium. In their elemental form, if you get them wet, they react violently. Then there are some boring atoms like calcium and magnesium and a few others. I guess these are okay atoms are things like fluorine and chlorine and iodine and bromine. And then we have all these lazy elements that really don't react at all. And those are kind of interesting. So I'll maybe talk about those a little more later. And then there's all the other stuff, the catalysts, the ones that are worth money, the ones you find in thermometers, batteries and coins like mercury and nickel and things. And then the weird ones, the radioactive ones named for America, named after smart people, fake elements made up by commies. Well, yeah, there's a lot of synthetic elements in this table that are, I think most of those are heavier than uranium. So we aren't really going to worry about those. Those are not elements that we like to have around living organisms. We'll put it that way. Okay, here's the actual periodic table of elements. That's maybe a little less informative. I actually like the other one because it kind of shows the patterns in that periodic table. But here we see carbon, and there's hydrogen, helium. The other ones that are interesting to life are maybe nitrogen and oxygen and phosphorus and sulfur. Then there's the salty ones like fluorine, chlorine, bromine, iodine. And then the other half of the salts like sodium and potassium. But if you have a periodic table, it will give you a lot of information about the atoms that make up these elements. So the atomic number is kind of the defining characteristic of an atom. And that is simply the number of protons in that atom. So for hydrogen, the atomic number is 1. So if ever there's an atom with just one proton in the nucleus, it's always going to be hydrogen. Then there's a symbol for that atom. So H is hydrogen. And then there's maybe a few others that start with H, like helium, and Hg is mercury, and I assume it's from some ancient Greek or version of mercury, right? So that is, sorry for my distracting phone. That is kind of the general information about these atoms. There's a name for it in most periodic tables. And then there's this other number, like right below the symbol usually, is this decimal number. And this is the atomic mass, or sometimes called the mass number for this element. And this is actually kind of a weighted average, or it's an average of all the naturally occurring versions of these atoms. And another way of saying versions is to say isotopes. So what this means is for hydrogen, its atomic number is 1, so it's got 1 proton in its nucleus by definition. But if we look at the mass number, it's a little bit more than 1. So there's usually 1 proton and nothing else, no neutrons, right? But every now and then we get a slightly different version of hydrogen that actually does have a neutron. And that's, they actually have a special name for this, these heavy hydrogen atoms. They call them deuterium for the ones with 1 neutron, and I think tritium for the ones with 2 neutrons, meaning that the deuterium has an atomic mass of 2 atomic mass units, and tritium, which has those 2 extra neutrons, or 1 proton and plus 2 neutrons, that would have an atomic mass of 3. So, and it's maybe about, if you have 1,000 hydrogen atoms, maybe 8 of them are deuterium, right? So they're just a little bit heavier because they've got a different number of neutrons. And so you can look at this periodic table. You can see like carbon here, its mass number is 12.01. So your average carbon atom, well, it's got 6 protons because that's its atomic number. And there's usually 6 neutrons because that's kind of the average for this, that average mass number is 12, right? So we know there were six of that average mass was the protons, right? And then the rest is going to be neutrons. So looking at these different elements, you can kind of figure out what a typical or maybe the most common version of that atom, the most common isotope. You can maybe deduce what the number of neutrons is based on this information. Okay, so I'm not going to say too much more about this whole periodic table because it's really more than we need. When we're talking about living organisms, like maybe ourselves, there's basically the kind of the big 4 elements, which are carbon, hydrogen, oxygen, and nitrogen. And together those make up, let's see, oh, I can't do math in my head, 75, 78, like 96% of our mass, we'll say, is these big 4 elements. And actually, it turns out oxygen is the most common by mass in our bodies because it's in water molecules, and most of our mass is actually water. So the next most common by mass would be carbon, because that's in every single biological molecule we have. So all the carbohydrates, the proteins, the lipids, the nucleic acids, which we're going to learn about in the next module, they all contain carbon. There's a really interesting reason why, but we're not going to get into that just yet. And then hydrogen, there's by number, there's probably more hydrogen atoms than any other in our bodies. There's 2 of them on every water molecule, and something like lipids or carbohydrates, there's going to be tons of hydrogen incorporated, but each hydrogen atom weighs almost nothing, like it's just 1 proton basically. So that's why the overall contribution to mass is pretty minimal. And then nitrogen isn't found in every different type of biological molecule, so that's why there's less of that. But there's still quite a bit of it. It's in proteins and it's in nucleic acids. So, and then, so that's kind of the big 4. And then after that, there's calcium, which is in our bones. There's phosphorus, which is in our DNA and also in our bones. potassium, the salt in our blood, sulfur, which is in some proteins, sodium and chlorine, again, the salt in our blood, magnesium, same kind of idea. So, and then a lot of trace elements that are, you know, kind of just in the things that we eat, and they also sometimes get incorporated into particular proteins. All right, so those are the elements that make up people and basically every other living organism. Okay, I wish this one showed up a little bit better. This is showing us the electron diagrams for the first 3 rows of the periodic table. So we've already seen that helium atom, right? So the helium nucleus, 2 protons, 2 neutrons, and then 2 electrons in this first electron shell. Hydrogen is kind of similar, except just 1 proton in the nucleus, maybe a neutron, but probably not, and 1 electron orbiting in this first shell. But it turns out there can only be 2 electrons that close to the nucleus. So these shells of electrons around a nucleus are kind of like energy levels. And this lowest energy level, the closest to the nucleus, doesn't have a whole lot of room in it. So it can only hold 2 electrons. For the next 2 rows of the periodic table, we have to add shells of electrons. So lithium, it's basically like a helium atom, and then you add 1 more proton and 1 more electron, maybe another neutron or 2. And this 3rd electron is all by itself in this 2nd shell. So this outermost shell for a lithium atom only has 1 electron. And then you add another proton to get beryllium, and you can add another electron to that outermost shell. But then you keep going with that, and you can actually add more than 2 electrons into the 2nd shell. It can actually hold a total of 8. So if we get all the way over here to neon, there's 10 protons in the nucleus, some number of neutrons that I don't know off the top of my head. There's 2 electrons in the first shell, and then 8 electrons in the 2nd shell. And this fills up that 2nd shell. So remember how we said that all the elements in this last column, the right-hand column of the periodic table, they're lazy, right? Because they don't react, they don't do anything. Well, the reason is because they have a full outer shell. And we call this the octet. Oh, come on, where's my next? Okay. Where's the color? Maybe that's why it's not showing up. The octet rule. So in general, atoms are happiest when they have a full outer shell of electrons. Okay, so all of these lazy elements, it's because they have this full outer shell. And all of the other elements are going to try to react in a way to fill that outer shell. So this is basically, we're trying to communicate a term's worth of chemistry, or maybe a year's worth of chemistry in the space of half an hour, 45 minutes, I don't know. But this is kind of the big picture, the big take-home message. Try to act surprised if you go on and take a chemistry class. But having these full outer shells is what makes atoms stable. The electrons are happy, so they don't react. It's very, very difficult to get these, we call them noble noble gases or inert gases, getting them to react with anything is very, very difficult. So, okay, so what about all these other atoms? Well, they're going to react in ways to try and end up with a full outer shell. And for the atoms that don't get these wet, like sodium, it has one electron in its outer shell, and then the next shell in has 8. So if it can just get rid of that one electron, then its outer shell is going to be full, right? And then what about chlorine? Chlorine has 7 electrons in its outer shell. So if it could pick up an electron from somewhere else, it's going to have a full outer shell. So when we get sodium and chlorine together, they react, and they react by sodium completely transferring its electron to chlorine to form ions, which are charged atoms or charged molecules. So sodium would form a positive ion because it's lost this electron, and chlorine would form a negative ion because it's gained that electron. And then they're happy, right? So this is how atoms react. Okay, I'm going to clear these annotations. I can go to the next slide. Okay, so chemical bonding. Chemical bonding is the result of atoms reacting. And there's basically 3 types of strong bonds that we're going to want to talk about. And these are the types of bonds that hold molecules or compounds together. And the 2 big categories are either covalent or ionic. Ionic bonds means that these electrons are completely transferred, like I was talking about with chlorine and sodium. And that forms 2 ions that are electrically attracted to each other, so it forms an ionic compound. So that's not really a molecule. When we put ionic compounds in water, they usually split apart for reasons that we will talk about. But they don't form distinct molecules. If we heated them up enough, we could break those ionic bonds. Covalent bonds, on the other hand, form when electrons are shared between atoms. So whenever you hear covalent, valence is a fancy name for the outermost shell of electrons. And when those outermost shells overlap, they are covalent. Okay. So those electrons can be shared equally, in which case we call them nonpolar covalent bonds. Or those electrons might be shared unequally, like one atom kind of hogs the electrons and has them more of the time, and those we would call polar covalent bonds. So, and I've got some examples of all these different types of bonds that I'll go through, and I'm sorry if the slide gets a little messy, but when we're talking about nonpolar covalent bonds, we can see that in a lot of elemental molecules. If we think about hydrogen gas, that's H2, or oxygen gas is O2, or nitrogen gas is N2. So when it's the same atom, it's got the same pole on those electrons, and those are going to be shared equally. The other time we see this is between carbon and hydrogen. If we ask each atom how much it wants those electrons, the answer is, about the same, actually. So when carbon and hydrogen get together, carbon can actually, it's got 4 empty spots in its outermost shell, and hydrogen has 1 empty spot in its outermost shell. So it can share electrons and form a very simple molecule like this methane molecule we see. And the carbon and hydrogen, those electrons are shared equally between those atoms. So that forms a nonpolar covalent bond. Okay, what about a polar covalent bond? Well, this is one we are very much familiar with because this is water. Turns out, if we look at the electron diagrams for water, we have 8 protons and 8 neutrons for your typical oxygen nucleus, and just a single proton for your typical hydrogen nucleus. And so what this means is oxygen has 2 empty spots in its outermost shell. Hydrogen has 1 empty spot in its outermost shell. And so there are these 2 covalent bonds between 2 different hydrogens and the same oxygen. So a very simple diagram. So we have our oxygen atom here, we have hydrogen here, and each of those, this little line here would be a covalent bond between oxygen and hydrogen. Well, it turns out when we ask each of these atoms how much it likes to hold on to electrons, oxygen says, ooh, a lot. Oxygen is an electron hog because there are 8 protons here, and that second shell is still pretty close to the nucleus. So any electron there is going to end up spending more time around those 8 protons than it will around this 1 proton of hydrogen. So this means that the hydrogen parts of a water molecule are weakly positive. It's not a full positive charge. It's not a complete transfer of electrons. Those hydrogen nuclei tend to stick around pretty well, but they don't get the electrons very often. Let me pause the recording really quick. I hear a knock on my door. Okay, so apparently I didn't pause the recording. Sorry about that. Had a interruption from my coworker, but anyhow, what were we talking about? We were talking about water molecules and how oxygen is an electron hog, and that makes the oxygen atom of a water molecule slightly negative in a couple of different places. And then the hydrogen atoms of a water molecule slightly positive. So this means that these bonds, these covalent bonds, this unequal sharing of electrons, that is a polar bond. And overall, we say that water is a polar molecule, which has some really interesting properties that we will be talking about shortly. All right. What about these ionic bonds? Here, the electrons are completely transferred. One of the atoms is such the electron hog, or the other atom is such the electron donor, or both, that these electrons are completely transferred from one to the other. And the example of that, I actually already mentioned it when we were looking at those electron diagrams in the periodic table. Sodium has this lone electron in the outer shell, and it will give that up very, very easily. And chlorine just has 7 out of 8 spots filled in its outer shell, so it will gladly take an electron from somewhere else. So what this means is sodium loses an electron and becomes a positively charged ion. Scribble on this. And then chlorine gains an electron and becomes a negatively charged ion. And we actually have some special terms for this, which I will mention them. So sodium would become a cation. So I'm going to put this over here. And the sodium cation is called sodium or sodium ion. And then chlorine becomes an anion. In this case, it's the chloride anion. So that's just the technical terms for whether an ion is positively charged or negatively charged. That's maybe a little more depth than we need in this course, but if you remember them, great. If not, just remember that they are both ions, and remember which one has the positive and negative charge based on which one has more protons than electrons and which one has more electrons than protons. Okay, clear those. Move on. Okay, so those were the bonds, those were the strong chemical bonds, but there's also some weak chemical bonds that are maybe don't last as long, and they're the kinds of bonds that we would form between molecules. So there's two categories of bonds. The stronger version of these weak bonds are called hydrogen bonds, and we find these a lot in water molecules. And what happens here is if you have two polar molecules that has a partially positive and partially negative region, I'm going to draw those on here. I'm going to use a different color. So I'll say that the hydrogens of a water molecule are partially positive, and the oxygens are partially negative. What this means is, I'm not drawing the little Greek delta to describe the partial charge, even though it really should be on there, but I'm lazy and I'm using my mouse to do this, so that would take a lot of time. But basically, there's a slight charge attraction between the hydrogen atom of one water molecule and the oxygen atom of a different water molecule. And this is called a hydrogen bond, and it is a very weak interaction. And in liquid water, these bonds are being formed and broken constantly. So these bonds are very short-lived. Now, if you cool that water down, the molecules aren't moving as much, then those hydrogen bonds can get locked into place, and you can form a crystal of ice where the hydrogen bonds are fixed and not breaking and reforming all the time. And if you heat water up even more, eventually you're going to break all of the hydrogen bonds, and the molecules are free to float away, and that's what happens when water boils. So these phase changes in water are really related to what's happening with the hydrogen bonds. How many are formed between each, for any given water molecule, how many hydrogen bonds are formed? If the answer is 4 and they're locked in place, you've got ice. If the answer is maybe less than 4 on average, but more than at least 1, then we're talking liquid water. And if we're talking no hydrogen bonds, then we're talking gas, right? Water vapor. So, okay. So that's what we have for polar molecules. And for non-polar molecules like oil or gecko's feet getting stuck to a wall, or even like Scotch tape, there are different interactions that work in kind of a similar way. It's this kind of instantaneous coordinated shifting of electrons that shift in complementary ways, where you get these very minute charge attractions between molecules. And if you get enough of them, then that can hold molecules together, but they are relatively weak. These van der Waals interactions, usually we're talking about lots and lots of atoms behaving in coordinated ways, which hydrogen bonds are just, 2 atoms on different molecules. So, okay, to clear off those notations. Okay, all right, so water is this polar molecule that can form hydrogen bonds. What does that mean? Why is that important for living organisms? Well, it is super, super important. The big, kind of the big idea here is that when we're looking for life on other planets, we start by looking for water, because water is so important to life here. And there are really kind of 3 properties, maybe we could stretch it to 5, but basically they all stem from water's polar nature. And this is an emergent property of water. So you know how we talked about those emergent properties when go from atoms to molecules, new things happen. Well, this is a great example of that. So water stabilizes temperature. It actually takes a lot of energy to break hydrogen bonds, and a lot of energy is released as hydrogen bonds are formed. And because of this, water has a very high heat capacity. So you might have noticed, like if you go to the beach in the middle of winter in Oregon, it's probably going to be a lot cooler than it is in Portland or Bend or somewhere like that. And that's because the ocean that is right next door is keeping the temperature relatively constant. The other mechanism for temperature stabilization, ice crystals, like ice, ice is actually a little bit less dense than water is when it's very cold. And this is because those hydrogen bonds are holding other molecules kind of at arm's length. So when we have a solid crystal of ice, like we see in this diagram here, the molecules and atoms are actually a little bit further away than if we have very cold water, where some of these hydrogen bonds are getting broken and reforming kind of on a very fast basis. So, and because of that, ice floats on the top, so we don't have lakes that freeze through. We don't have oceans freezing solid to the bottom. Without this floating ice, we would probably be restricted to just the equatorial regions would have liquid water on Earth, and much less opportunity for life to establish itself and diversify. The other interesting property of water is that it is a great solvent, sometimes called the universal solvent, although it's not really universal. It's a great solvent for hydrophilic substances, which could be polar molecules or these ions, right? Like the sodium and chloride ions. It doesn't do great with hydrophobic molecules, which is to say non-polar molecules. So hydrophobic substances have a lot of non-polar covalent bonds, things like oils and fats, and they don't mix with water very well. In fact, there's a saying about that, right? Oil and water don't mix. And the reason is because the oil is hydrophobic and cannot be dissolved by these polar water molecules. Well, how do those water molecules dissolve hydrophilic substances? And it's pretty simple. We have a water molecule that's got a slight negative charge on the oxygen, slight positive charges on the hydrogen. And if they surround a negatively charged ion, like the chloride anion, the hydrogens are going to surround that in this, we call it a sphere of hydration. And so these water molecules surround it and dissipate that charge, and then these water molecules get hydrogen bonded to other water molecules, and we kind of have this extending spheres of hydration around these ions. For the sodium ion, that cation, that is going to attract the slight negative charges on the oxygens. And so water molecules are going to flip around when they come close to a sodium ion, and again, form these spheres of hydration that dissipate that charge and allow it to be dissolved into the solvent, right? So if you have a large volume of water, you can dissolve salt into it. You can dissolve sugar. Sugar is another polar molecule. And we'll talk about this a little bit more in the next module, but just want to mention that here. And lastly, water has this property called cohesion, meaning it sticks to itself. So you can form droplets of water that can precipitate down from the sky. You can have surface tension on the surface of a water. You know, you could have water striders that could live on that. And you could also have plants sucking up water from their roots to their leaves through the cohesive nature of water. And then water also has this property called adhesion, which means that water will adhere to or stick to hydrophilic substances. So again, kind of like what we saw with this solvent property, water can stick to other things as long as they're either polar or charged. And so this is important, again, when we talk about how plants get water up to their, from their roots up to their leaves. Adhesion is a big part of this. But we'll talk about this more in the week 3 lab. We have a whole lab all about water. So won't say too much more about that now. All right, the last really interesting property of water is that it can split apart and form these ions called either hydroxide or hydrogen ions. Let's see, I'm going to draw this. So, so we can have H2O, which can split apart and or reform. I'm going to put a much bigger arrow for the reforming into these 2 different ions, the hydrogen ion or the hydroxide ion. And so usually this doesn't happen very often. Usually if these ions meet up, they're going to react to form a water molecule. It's more stable. And there is that sharing of electrons, even if that sharing is unequal. But it turns out you can add things to water to change this balance. So if you add things like hydrochloric acid, that's going to release a lot of hydrogen ions. And so we have a much higher concentration of hydrogen ions in that solution. Or we could add something like drain cleaner or lye, sodium hydroxide. We could add a bunch of hydroxide ions, and that's going to shift the balance the other way. So when we say neutral at pH 7, that means that there's a balance in these hydrogen and hydroxide ions. If the pH is lower than that, there's kind of an imbalance so that there are more hydrogen ions than hydroxide ions. So we would say that's a low pH. pH is just a fancy shorthand for the concentration of hydrogen ions. And if we add more hydroxide ions, we would say it's a high pH or a very low concentration of hydrogen ions. So actually, I'm going to make a few more notes on this. So for acidic substances, we have more hydrogen than hydroxide. And then for alkaline or basic solutions, we have more hydroxide than hydrogen ions. Okay, so what this means is things that are acidic, we've got an excess of hydrogen ions, and that changes the environment for cellular biochemistry. Our cells actually like to be a little bit basic. Blood has a pH of, maybe 7.7, somewhere around there. Just very slightly basic. Seawater, well, if we were back in 1870, the pH would have been 8.18. In 2100, it's predicted to be quite a bit more acidic. Still basic on the big scheme of things on this pH scale, but less basic. That's a word. So more acidic. And that's because of all this carbon dioxide that we are putting into the atmosphere, which some of it dissolves in water, and that actually adds hydrogen ions to that water, and that changes the balance. So I guess the arrow should be going the other way, based on this screen. Okay, never mind. Anyhow, all right, so this means that the ionic balance, the balance of hydrogen hydroxide ions is very important for the biochemistry that happens in these water-based solutions. And usually living organisms have a system of buffers to keep the pH constant. When we talk about homeostasis, maintaining internal conditions, one of them is pH. And for humans, if our blood gets a little bit acidic or a little bit basic, we die. And it doesn't have to be a big change. It's not going from, just a little more basic than neutral down to just even slightly acidic, like pH 5, we're dead. pH 6.5, that's severe illness. So we can't tolerate a huge swing in pH values. So we have to have buffers to do that. And basically buffers are weak acids and weak bases that will combine and scavenge up extra hydrogen ions or extra hydroxide ions, depending on the situation. And they'll do this kind of at the same time. So there's a whole buffering system that we use in our blood that involves bicarbonate and carbonate, or bicarbonate and carbonic acid, and breathing is actually related to this. So by breathing, we actually get rid of the extra acid. We don't need to go through the whole mechanisms and chemistry of that, but just be aware that living organisms are going to try and keep the pH constant. Okay, with that, I am out of breath, and hopefully this video, I know it's going to be long, but I will try and chop it down to be shorter, and I will see you on the next one. Bye. Stop that. Okay.